In this particular lecture, we are going to do some worked out examples on the forced convection. So that we have finished the forced convection module, internal and external forced convection. So we will look at some of the sample problems, mainly from Adrian Bejan, and we will provide you with a kind of a worked out examples of those problems. Okay, so the idea behind this is that you should get an idea to approach how to solve different problems which might come in handy during your exams and during your industrial calculations in whatever profession you are involved in. So, you can consider this to be a forced convection tutorial. Okay. So, the first problem in this particular series is basically, if you read the problem statement again from Adrian Bejan, an isothermal flat strip, okay, is swept by a parallel stream of water with a temperature of 20 degrees Celsius and a free stream velocity of 0.5 meter per second. The width of the strip is about 1 centimeter parallel to the flow. The temperature difference between the strip and the free stream is delta T equal to about 1 degree Celsius. So, the things that we need to calculate is the L averaged shear stress, okay, and the L averaged, that means the length and the width averaged shear stress and the averaged heat flux between the stream and the water flow. So, that is what the problem statement is all about. So, let us see that how we can attack and solve this problem. Okay. So, moving to our journal. So, let us call this problem A1. Okay. So, this is the problem statement. Okay. So, first and foremost what we need to do is that we need to compute some relevant properties, because it is given that the working fluid is water, okay, at 20 degrees Celsius and atmospheric pressure. Okay. So, some of the properties. So, rho for example is coming out to be about 0.997 gram per cc. Prandtl number is about 7.07. Okay. The kinematic viscosity is about 0.01 centimeter square per second. K is about 0.59 meter per watt per meter Kelvin. Okay. So, that is in general the properties of water. Okay. So, the L averaged shear stress, which is tau WL or tau wall L, can be calculated in the following order. Okay. So, tau L is equal to half rho u infinity square CFL, skin friction coefficient, right. Okay. And we know what the skin friction coefficient is all about, rho u infinity square, okay, 1.328 Reynolds number to the power of minus half, right. This is the relationship that you already know from your analysis of a flat plate, right. Okay. So, where the Reynolds number in this particular case is given as u infinity L by gamma, okay, which is about 0.5. Remember that the velocity was about 0.5 for water, that was the velocity of water, okay, and 1 centimeter was the length. Okay. So, and it was about 0.01 centimeter square was the kinematic viscosity. So, this roughly translates to about Reynolds number of 5000, which is in the laminar range. Okay. For an external boundary layer or external forced convection, the transition to turbulence happens much later. Once we do the turbulence part of this particular course, we will know. Okay. But as of now, this is a very simple calculation where we did find out the wall shear stress as well as the Reynolds number now. Okay. Now, based on this, let us move to the next one. Okay. So, now you can find out tau wall, okay, you basically it is a plugged in values of all these numbers. So, basically you have half into 0.997, that is the density, okay, into, and you just do the unit conversions also, which I am not showing over here, okay, 1.328 into 5000 to the power of minus half, something like that. Okay. So, it will come out to be approximately 0.00234 gram meter square centimeter cube second square. Okay. So, that if you convert it to the more traditional unit, it is coming out to be Newton per meter square, 2340 newtons per meter square. Similarly, the L averaged heat flux, okay, that is given as Q bar double prime W comma L K delta T by L, Nusselt number L bar, that is given as K delta T by L 0.664, Prandtl number 1/3, Reynolds number half. So, this is the standard. So, we already are given that delta T is about 1 degree Celsius, if you recall the problem statement. So, 0.59, okay, this is watt per meter Kelvin. It is a good exercise to write the units, so that you do not encounter any problem. Either you convert it to the same unit, okay, or you do it at the end, okay, whatever, but then in that case you should write all the units down. Prandtl number is 7, we already gave that. Okay. So, this comes out to be about 5317 watt per meter square. Okay. So, you can see that so it was a simple problem that we are able to solve just by using the correlations that were available. What correlations we used? For the average Nusselt number we used that correlation, okay, and for the average wall shear stress we used the other correlation. So, basically you can either use the similarity solution. From the similarity solution you have these numbers already at your disposal, or these correlations at your disposal, or you can also use the the integral formulation, use that also, because the constant is only going to vary within 10%, right. Okay. So, this constitutes our first problem in the series. Okay. Let us do the second problem, which is a little bit more complex than the first. Okay. And so, we start with a easier problem and then we slowly ratchet it up a little bit, so that we see that how this problem actually works. Okay. So, in this particular case, look at the problem statement very carefully. Okay. So, here what we are considering is the development of a two-dimensional laminar jet discharging in the x direction. So, this is x and y, this is x, that is y, okay, into a fluid reservoir which contains the same fluid as the jet, right. The reservoir pressure P infinity is constant, okay, and the jet is generated by a narrow slit of width d naught. This is the narrow slit. Okay. The average fluid velocity through the slit is u naught. Okay. Now, if you look at this particular problem very carefully, okay, you will find that first and foremost a few things. This problem, where is it encountered? For example, the smoke that is coming out of the tailpipe of your car, that is very similar to this, because though of course that contains carbon monoxide and others, okay. But here if you imagine that air is coming out into a body of air, this is almost a problem like this. So, there is this and you get the flow coming out like that, right. So, it is say example, this is air, this is also air, both can be water also, it can be any other fluid, but it is the same fluid combination. So, that means one fluid is coming into another fluid where both the fluid types are essentially the same, right, and this opening is very small compared to the extent of your reservoir in which it is getting flushed, right. Okay. So, this is a very typical problem of a laminar jet. It is a 2D laminar jet because it is like a slot. These are like slots, right. Okay. So, it is coming out through this slot basically. Okay. So, that extends to infinity, obviously whatever is in the direction perpendicular to the board, right. Okay. Now, we have sketched something up over here to just give you an idea that how will the flow velocity actually look like. We know that it is coming out with a velocity u naught, which is constant. Okay. So, as the velocity, as the jet actually spreads, okay, in the radial direction, okay, you can imagine that the velocity should slowly drop. Okay, it will no longer, here it is almost like a top hat kind of a profile, right. So, as you go here at any particular cross section, you expect that this would be the kind of a profile that we have drawn over here. Okay. So, the jet will actually, because the area, okay, is actually increasing, as you can see by those dotted lines, the area is actually increasing. So, naturally the jet will decay, right, and the center line velocity is going to come down and it is going to assume some kind of a profile like that. What is that profile? That is an interesting question. So, if dx and ux are the jet thickness, right, that means the thickness means this is the thickness, and the center line velocity, which is ux, okay, is the center line velocity is this guy over here, right, okay, at a sufficiently long distance x from the nozzle, that means it is not in the near field, okay, it is not in the near field. So, relying on the mass and momentum conservation equations on boundary layer theory, okay, and on scale analysis in a flow region of length x and thickness d, determine the order of magnitude of d and u in terms of d naught, u naught, x and the kinematic viscosity, and this is the solution that we need to find out. Okay. So, there is a hint also that is given that you need to integrate the momentum equation, okay, from at any x, that means at any particular plane you have to integrate it out in the y direction, okay, and this can result in some additional scaling laws, but these are scaling laws as you can see over here, and we have to take care of these scaling laws and we have to find out that how this jet actually kind of behaves. Okay. So, this is the problem that we have posed. It is a little different from what you have right now. So, let us check that how this is going to be solved. Okay. So, this is a little bit more difficult problem than what we had earlier. Okay. So, let us chalk out the jet a little bit. So, it is u naught. Okay. So, this is coming out like this, and this is at any cross section, given cross section. This is what the profile actually looks like. This is the corresponding u center line velocity. Okay. So, this is basically your u and v. This is the profile, this is your x, okay, and this is your y, okay, and this is basically your d naught, which is basically the diameter or the opening of the jet. Okay. So, for a two dimensional laminar jet, okay, using this as a slender flow region, so we can write the continuity equal to 0. Similarly, the momentum, okay, and this will be the momentum that we are going to write in the x direction. So, the x momentum, and we have applied the boundary layer approximation. This comes from the slenderness of the jet or slenderness of the flow region. Okay. So, this particular term, as we know, this is given as dp by dx is the same as dp infinity by dx should be equal to 0, because p infinity is equal to a constant. Okay, is equal to a constant, right. So, now if we apply the normal scaling arguments, so from the continuity equation you get u by x, okay, u by x will scale as v by d, right. That would be the first scaling that you will have from the x momentum equation, as we know that these two terms usually will be of the same scale. Okay. So, you can write it as u square by x, right, scaling as gamma u by d square. Okay. So, this gives us the equation as u d square is proportional to gamma into x, right. So, that is the entire thing we get. So, this is the relation number 1, let us say, first relation that we get. This is nothing uncommon, this is what we got in our traditional flat plate boundary layer equation also. Okay. Assuming this is a very similar looking equation, right, there is nothing very drastically different about it. Okay. We have still applied the same slenderness or the boundary layer type of concept over here. Okay. And of course, we have taken the dp infinity by dx to be equal to 0, because we already said that it is flushing into a reservoir where the pressure is constant. Okay. Now, the second relationship, okay, second relation between, you need a second relation between u and d, that is because you have one relation, there are two unknowns, you are supposed to find out two scales for u and d, one for u, one for d, and you need another equation, period, right. Okay. So, uniquely follows, so second relationship uniquely follows, that is the hint that we gave. Okay. So, let us take the x momentum equation and let us do it like this. Okay. So, integrate at constant x, okay, at constant x from y equal to minus infinity to y equal to plus infinity. We are integrating the whole thing. Okay. So, you have d by dx minus infinity to plus infinity u square dy plus u infinity v infinity, right, that is the first term, minus u minus infinity v minus infinity, right, okay, that is equal to gamma du by dy y equal to infinity evaluated minus du by dy at y equal to minus infinity, right. So, we have taken a section which you can see over here, okay, and we have basically integrating out across this particular direction, okay, that is minus infinity to plus infinity, got it. So, based on that you can see that most of these terms are actually equal to 0, this is 0, this is 0, this is 0, this is 0, because of the far field everything vanishes, right, it is a far field. So, at y infinity is a reservoir which was initially quiescent, right. So, everything should vanish at the far field. So, similarly things have vanished in the far field, this has vanished, this everything kind of vanishes in the far field. So, all you are left with is d by dx minus infinity to plus infinity u square dy is equal to 0. This actually leads to minus infinity to plus infinity u square dy equal to u naught square into d naught, okay, that is equal to a constant, must be, because why this is so, this is equal to 0, that means this must be a constant, and what can that constant be? The constant should be the initial momentum that you are flushing out, and what is the initial momentum? Initial momentum is u square d naught, right. So, that is the initial momentum, that is the initial momentum of the jet as it comes out of this nozzle, right. So, because this is integral, this is like a constant momentum source, the jet is like a constant momentum source. So, any integral formulation, okay, that has to conserve whatever initial momentum that you have flushed in, right. Okay. So, when you apply the scaling law to this, okay, so it will be u square into d should scale as u naught square into d naught, that is your second relationship that you have got using this additional scaling argument that the jet is a constant momentum source, right. So, now you can combine the two relationships, one is u d square scaling as gamma x, the other one is u square d scaling as u naught square d naught. So, we have two expressions, we have two unknowns. So, it is very easy actually to do. So, d scales as gamma 2/3 x 2/3 u naught minus 2/3 d naught minus 1/3, right. And similarly u scaling as gamma 1/3 x minus 1/3 u naught 4/3 d naught 2/3. Okay. So, you get the expression. Now, you can do the algebra and you can get the forms that we actually mentioned over there, okay, d by x and other things that we mentioned. If you look at what the question was, okay, you can cast it dx by d naught in that kind of a way. Okay. So, that is left as an exercise. So, we have derived the main things from this, right. So, it was a very simple thing. First we did the scaling, a simple scaling argument. Next what we did was that we used the fact that the jet is actually bleeding out into a constant, it's like a quiescent reservoir. As a result, far field quantities vanishes. Okay. So, the only thing that is remaining is that the momentum of the jet, the initial momentum of the jet is actually is a constant momentum source. So, equating those two, we related u and d to u naught and d naught, and we found our crucial second expression. So, now you can take this problem further, you can also apply it to a temperature field. Okay. Now, you can see several things. For example, the u of the jet shows x to the power of minus 1/3 decay, which is kind of logical, right. That means with x this should actually decay, the center line velocity should actually decay, right. So, that is one important expression that we get, okay. And the jet diameter increases by x to the power of 2/3. That is also an interesting observation, right. So, that means the jet core expands and the jet center line velocity decays. Okay. So, the jet core expands as a 2/3 of x. That means, as you march on to x, the core of the jet expands in that 2/3 way, whereas the velocity of the jet, the center line velocity of the jet decays as 1/3, minus 1/3 of x. That means, it is as x increases, this actually decreases, right. So, that is kind of very logical, because we know that the center line velocity at different sections, if I just plot it like this, it will be like this, then it will spread out, obviously, it will look like that. Okay. So, there is a decay, and this decay in this direction x actually is going up, right. Similarly, the core diameter of the jet, as you saw over here, the diameter is different from that. It is almost like that boundary layer growth, right. So, d decays, increases with x increase, whereas u decreases with x increase, which is kind of very logical, okay, from the diagram that we drew in the previous statement. Okay. So, if you, so just to recap, okay, so this was the way that we solved the problem, that this was a constant momentum source, that was the argument that we put forward, this was the kind of the profile of the jet, very simple. Continuity, you get this, from the momentum you get this. Okay. We needed one more equation connecting u and d, because there were two unknowns. Okay. So, naturally what we did was that we took the we applied an integral formulation to this particular equation, the conservative form of the momentum equation, and then we cancelled most of the terms because of the far field nature of the thing. We came across to this expression, and from there we got the key relationship, the second relationship, which is basically says that the jet is a constant momentum source. And based on this, we have basically found out these two crucial relationships, which also implies that d increases with x, which is logical, and u decreases with x, which is also logical, and they decrease and increase in that 2/3 and 1/3 fashion. Okay. So, these are some of the crucial things that we did in this particular lecture. We will now look at a slightly different problem. These were both on external forced convection. Okay. So, we in the next one, which we are going to do, will be on internal convection, because internal forced convection. Okay. So, that is what we are going to do in the next class. Thank you.